Welcome back to CS520. In this session, I just want to talk a little bit about Program 2. You should be completing Lab 4 soon or already, hopefully. And that was the phase that we built a symbol table. Program 2, as you know, is to build an assembler for VM520. And I guess it's Lab 5 next week is to do really the first pass of the assembler, which is to get the labels into the symbol table. So I just want to run through a few things, a few details, just to help you get started if you've been struggling a little bit with this assignment. Again, the big picture was covered in the lectures, but let's just quickly review it here. You know, the assembler, pass 1 of the assembler is to determine the addresses for the labels that are defined in the program. Again, this is to solve the forward reference problem. Pass 2, then, we actually output the object code because now we know everything we're going to know. We know all the addresses of any label that's been defined. And also along the way, we got to keep track of simple information that's going to go into the object file. This is the in symbols and the out symbols. And finally, there's a responsibility to do error checking. The user may not always give us a correct program. So the assembler is working to detect those errors as well. All right, so that's the big picture. Again, if you haven't seen the videos on assembling assembling for VM520, you need to watch those and make sure you understand the concepts. Today, though, I'm just going to dig into some of the details. And the key thing here is it's somewhat of a realistic project. You're not writing all the code. I'm writing a lot of the code to do the input and parse the input. But that means you and I have to agree. So you need to work with the code interfaces that I have defined. And actually, I've set things up so you only have to write 3 functions. Of course, there's a lot of work in some of these functions. So what are these 3 functions? Init assemble is called once. So that's your chance to initialize any of your data structures that you're going to need. And for instance, you're going to create a symbol table using your Lab 4 code. And this symbol table will be used later to store labels and addresses. But in the init symbol, you can create that symbol table. Then the assemble routine is called for every line of input. Not quite true, but roughly true. Every line of input that you need to see. My code will strip out the comment lines, for instance, and the blank lines. You won't see those. But I'll call you for every meaningful line of the user's input program. And this routine is used on both the first pass and the second pass, and maybe that was a mistake in this design, but it's too late now. So you're going to have some way to determine when I call the function assemble, whether you're on the first pass or second pass. And the way you know is that when we cross between passes, I will call between passes and let you know that we're done with pass 1. So what you'll probably want to do is have a global variable or something that will remember when between passes has been called, so that you know subsequent calls to assemble are for pass 2 when we're reading the file the second time. Just quickly, I think we'll see this again in a minute, but the symbol takes 2 parameters. One is a label, if there is one being defined. So this would be a label with a colon after it. And the char star, of course, is the ASCII string for that label. And then there's a struct called instruction, essentially. It's a struct type, and we'll talk about that, the details of that in just a minute. Between passes gives you a file star. This is something to be passed to putc or to fprintf when you're actually, I'm sorry, not fprintf, you'll be passing this to putc to output the actual bytes of the object file. So I open the file, I create all the files and everything, and you just have to write bytes to this stream. All this stuff, this interface, is defined in the header file defs.h. Let's take a look at that next. defs.h, starts with some comments. And of course, you should read over these. I'll try to briefly explain it to you as we go along. Let's dig into the details themselves. Again, the interface that we just looked at is specified here. This is what you're implementing. Below the line here are error message routines that you will use when you detect errors. You should route your error messages through this so that the assembler has a consistent interface for the error messages to the user. You're usually going to want to be doing calls to error. This is what I call semantic errors. So the program is structurally okay, but the pieces don't make sense. So for instance, if I say, an example here, if I have an instruction, it just says add I. In other words, user forgot to put registers. That's what I would call a semantic error. My front end of the assembler will parse that okay, but then when it hands it to you, you need to realize that add I expects a certain format. It expects 2 registers to be provided, and then you will issue an error message through this function. This function has an interface like printf, or not like printf. So there's a format string and then a variable number of arguments that you can provide. So it's a printf-like format. Okay. You might also use the fatal and the bug. These are for internal errors. So if your symbol table runs out of space, you can't create it, you can't add a new entry. If the symbol table is failing, then you would probably call the fatal message, which will actually terminate the assembler. Hopefully these things won't happen, but you need to always be wary of malloc running out of space or whatever. Okay, and then bug would be called if you have an internal check, a sanity check in your code, and you realize something internally has gone wrong. You can issue a bug message. Again, the bug message will shut the assembler down. Again, these will have different output formats, and this technique of having standardized error messages is a good idea. And then separating out, user errors from internal errors is a good idea. It'll help you debug the system. This last function I call when there's actually a syntax error on the input, so you probably can ignore that. All right, the last part of defs.h defines this instruction struct. Again, it defines the type instruction, which is the second parameter. Let me just go back to the interface. It's the second parameter of the assemble function. Remember, the first parameter will be a label being defined. The second parameter will be an instruction. You could have lines without labels. You could have lines without instructions. Okay. All right, so let's look at this. This is a complicated struct. The first thing is it always has a format field which tells you which of the 9 formats it is. And I'm guessing, I should have looked this up before I started taping this video, but I'm guessing format 0 means that there is no instruction present. Right, that's what it means. I just checked my code. So you have there's actually, if you look at the VM520 documents, I think there's 8 specified formats at the hardware level. There's a 9th format here because of the directives, which aren't instructions. They're not actually represented at runtime, but we need to be able to process them. So in particular, the alloc directive, example is something like that. Its format is, everybody has an opcode, of course, or something that looks like an opcode, and in this format there's just an integer constant. Okay, I guess this one also shows up with Word, right? I can say Word 99, it's the same thing. So there's a 9th format here to handle those 2 directives. So anyways, that's the first field. The first field tells you the format, and again, let me write here if 0 it means there's no instruction present. Because the user might put a label on a line by itself. My programming style actually does that quite often, so you're going to see that in the test programs. Okay. Second field is the opcode. Again, it's a char star. And then the third field is this union. Is this union where there's a member of the union for every format. Notice format 1 is missing because format 1 is simply just an opcode. So there's no additional information to carry there. But for formats 2 through 9, there's additional information. What's a union? A union is a struct where the members are all sitting on top of each other. So they don't take additional space. They don't concatenate to each other. They just lie on top of each other. So you use unions in situations like that where you have a format and then you have different kinds of data that would be present depending on which format is present. So if I look in the format field and I see a 2, then I know that there's going to be an address. An address in this case it would be a label reference. Or if I see format 7, I know there will be 2 register numbers given. Okay, so that's the use of a union. Again, a union is a struct where the members all lie on top of each other in memory. So you usually use a union with a control field that tells you which member of the union is active at any point in time. Let's take a look at this. If I, if the parameter to assemble, the instruction parameter to assemble is called lowercase instruction, then I might write things like this, right? I can refer to the format in the usual way. Instruction.format. Make a note that the interface is not maybe what you think it is. It's an actual struct being passed here. It's not a pointer to a struct. So consequently, you're going to want to write expressions using the dot. Instruction.format, instruction.opcode. Okay. Then what if you want to look at a particular format? So let's assume that the format is 9. We look in there and we see a 9. I might want to write something like this. Instruction. In this case now it's .u. I have to choose the u because u is the name of the union. Again, this is just a coding style that I've developed myself, but the union has a member name. So I have to select the union. So instruction.union, then another dot to select a particular format. And let's say I want format 9. Right, I want to select U and then format 9 and then the member of format 9, which is constant. T-A-N-T. Okay, so that's what that's going to look like. There's going to be a bunch of dots in there. So that's how I pass information to you. I'm going to tell you, what format the code is that I saw, what the opcode is, and then for particular formats, the details of that format. Again, note that this is what's in the source code program, and so you could have mismatches. So another error check that you have to do is I might say something like add I and 99. That's going to parse, in my part of the code, that will parse okay. That looks okay to me because I don't know anything about the semantics. But you've got to go in and validate that. What does add I? Add I is going to come to you as format 9, but that actually is wrong, right? Add I should be format 7. So this is the part of the error checking that you're going to have to do. I'm sorry, format should be format 8. It should be 2 registers. Okay, so make sure you understand that. If you don't understand that interface and how that union works, please raise questions on Piazza so we can get them addressed. What else? Well, let me just some other thoughts about how to approach this assignment. You've got to validate opcodes. Again, the user program might have errors. They might have something that looks to me to be an opcode, but it's not one of the valid VM520 opcodes. So I will parse it. It looks syntactically okay, but you have to validate that it's actually one of the VM520 opcodes. So to do this, you either can have a series of if statements using string compare to compare the opcode string that I give you through the interface as the first parameter to a symbol, and one of the valid opcodes, and you could just go through a big series of ifs. I don't know how many opcodes there are, 15 or 20. So you'd have this big complicated if statement. The alternative would be to use a hash table, actually, to use your code from Lab 4 in a second way. You know already you're going to use it to store labels and their addresses, but you could have a second hash table. That's the beauty of our Lab 4 code. We didn't create one hash table. We created a facility for creating hash tables. So you could have a second hash table in which you install all the valid opcodes and the directives like alloc and word. And then when I give you an opcode string, you can look up that opcode string in the table that you've created of valid opcodes, and if it's present, it's valid. If it's not present, it's not valid. And moreover, you could store as the data associated with the hash table entry, you could store whatever you need to know about the opcode, like the expected instruction format, that add I expects format 8, and if you don't get format 8, it's an error. I don't really know which one of these two is better. I mean, this one, you have this big series of if statements. This one, however, you're going to also have some complicated code when you go to do the install into the symbol table at initialization time to install all the opcodes. So I think probably either approach is reasonable. All right, what other thoughts do I have? Just want to make sure that you understand all instructions on this machine take one word, so that's simple. The word directive also takes one word. In other words, you're going to output one word into the object file for each instruction and one word into the object file for the word directive. But note that the alloc directive is a little different. You're going to output the number of words specified by the directive itself. So if the user says word 10, that means you're going to output 10 words into the output file, into the object code file. Another special case is the import and export directives. They actually consume 0 words. They're just information to the assembler. We'll talk about those a little bit more next. So what does import mean actually? Import means a symbol should be used somewhere in the program. The symbol should be used, but it's not defined anywhere in the program. So we're importing that symbol into this program. It would be an example in real world would be printf, right? We call printf, but we don't define printf. Export is sort of the reverse. It should be a symbol that's defined in this program that we want the outside world to know about. So we're going to export that to the outside world. So, in the case that we are writing printf would be exported from our code. So when you go to generate the object file, you have to generate in symbol and out symbol information. Well, the out symbols are exactly the imported symbols, and the in symbols are exactly the exported symbols. So whether a symbol is imported or exported needs to be tracked in the symbol table, so that when you go to write things out, you know exactly what you need to know. Okay, so when you see an import directive, you're probably going to install something in the symbol table to say the symbol that's marked by the import, the symbol that's named in the import directive will be marked in the symbol table as being imported. And same thing for exported symbols. They'll be marked in the symbol table as being exported. One other thing about out symbols, notice that the out symbol information you need to output to the output file needs to track all references, right? All references to an out symbol. So you're probably going to need a linked list emanating from your data field attached to a symbol table record for an imported symbol, because you have a responsibility to issue an out symbol record for each reference. So you need to know where all those references are. So again, you're going to have to build a data structure, probably a linked list of all references to a given symbol. Okay, I think that's what I wanted to say. So please, review those thoughts. Try to get started early on this Lab 5, and please post your questions, Piazza, so we can get them resolved and help everyone else. Because if you have the question, probably someone else does too.